come from Luca, or so the thinking goes. So many researchers who study Luca are trying to reconstruct its genome. One way they do that is by finding what they call the minimal genome, the smallest amount of genes that a cell can have and still survive. Since these most basic essential genes are thought to have come from Luca, if we could identify them, that would tell us how Luca looked and lived. This work has been spearheaded mainly by researchers in Maryland who have studied the genomes of bacteria like Haemophilus and Mycoplasma. And based on what those organisms have in common, the team proposed back in 2003 that Luca probably had 500 or 600 genes. Those genes would have provided for a simple metabolism and a genome based on RNA, but not for making and copying DNA. Now, as genomes go, that is tiny. A few modern organisms do have about 500 genes, but they are parasites that steal what they need from their hosts instead of using genes to make stuff. Meanwhile, the bacterium E. coli has around 5,000 genes. In humans, we get about 25,000. So could Luca survive on its own with so few genes? Well, another study done in 2006 found that Luca would likely have had more like 1,000 genes, maybe around 15 or 1,600. According to this slightly more recent take, our common ancestor might have been a little more complex and may have seemed a little more familiar to microbiologists, at least. That means a genome based on DNA, ribosomes to translate the genetic code, and a metabolism that could break down sugar for energy. So the basics of biochemistry as we know it. And Joe talks a lot more about that too on It's Okay to Be Smart. Now, a lot of this minimal genome research took place at the turn of the millennium, around the same time Woese was thinking about Luca. But in the last 20 years, the genetic revolution has redrawn the tree of life. Recently, many scientists have begun to argue that the tree of life should have two main branches, with bacteria on one branch and archaea, plus all of the eukaryotes on the other. That's because the more we learn about genomics, the more it seems that all modern eukaryotes are genetically more similar to archaea than to bacteria. In fact, many researchers now believe that archaea are our ancestors. So of course this has enormous implications for what Luca was too. In this case, Luca would sit just below where those two main branches separate before eukaryotes even formed. And based on this new line of thinking, a surprisingly complete picture of Luca was published in 2016 in the journal Nature Microbiology. Here, evolutionary biologists based in Germany compared the genomes of more than 130 archaea and over 1,800 bacteria in an attempt to reconstruct Luca's genome. Keep in mind here, in the two-branch model, archaea and bacteria are the most distantly related forms of life on Earth. So if you can find any gene in both archaea and bacteria, then there are two possibilities. Either the two groups traded genes at some point, which prokaryotes sometimes do, or they both inherited that gene from Luca. The researchers looked for genes that appear in two different groups of archaea and two different groups of bacteria, reasoning that if a gene shows up in all four of those places, it must go back pretty far. Now, this is different from the minimal genome approach because it tries to identify the oldest genes, not the ones that everyone has. And the genes that were recovered in this research suggest that Luca lived in hydrothermal vents. How do they know? Well, for one thing, they recovered a set of genes that we know are used by extremely ancient groups of archaea and bacteria that live in oxygen-free environments where they metabolize hydrogen gas and carbon dioxide into methane. Hydrogen gas is hard to find on Earth, but it can come from deep-sea vents, so that's one clue. Other genes they found need metals like iron, nickel, and molybdenum in order to function, and these are all found in the same kind of environment as hydrothermal vents. Scalding hot vents full of metals and sulfur might seem pretty hostile, but our earliest ancestor might have called these places home. Now, how could that be? Like, we don't metabolize hydrogen and CO2 into methane, and neither do most of the organisms we know. So how could the ancestor of everything have been so different from us? Well, it's at least possible, because genes are often lost over time. As creatures evolve and adapt to new environments, lots of old genes aren't always needed. That's basically why cats have genes to make fur, and not genes to make scales. So by the same token, long after molecular oxygen became available on Earth about 2.5 billion years ago, many of Luca's descendants were able to lose the genes for metabolizing hydrogen and CO2 and still live comfortably. Now, as awesome as this picture of Luca is, it's only one possible picture. It'll be a long time before we know enough to agree on one single model. both the progenote model and the minimal genome idea have proven useful to guide our thinking.